Yeah, Amma, what did you get for tea?
Sir, please, I got 1 second.
Good, good. Once you have, Agosia, your hand is still up.
Answer. Sorry, the same answer. Sorry.
Good. And once you have the time, you can easily calculate for the vertical height where the two stones would cross each other. Okay, so go ahead and then make me proud. Calculate it for me where the two stones crosses each other. Agosia, I know. Once you have once you have T, the other one becomes so simple. I guess you had 25.
Yes, please.
Yes. Mhm. Yeah. So 8 becomes 25. Quickly, for the benefit of those who perhaps had a challenge in solving it, we have the first equation to be H to be equal to 30 T minus 5T squared. Then the second one to be um let's quickly make H the subject from equation 1. And we have H being equal to 30 minus 5T squared. So when we equate, okay, we have 30T minus 5T squared being equal to another 30T minus 5T squared. Okay, when we group, sorry, I think this is 30. When we send this to the other side, this will reduce to 0, so that we have 30T to be equal to 30. T therefore is equal to 1 second. Once T is equal to 1 second, using any of the equations, you can find H. So H becomes 30 minus 5 by 1 to be equal to 25 meter. What it means is that the two stones will cross each other at the 25th meter. Okay, so Kelly, you see, as I told you earlier, that you cannot assume until you have gone through the calculation. 25 meters is more than half as you assumed earlier. So when you have a situation like this, the best way is to represent the unknown by a variable, apply the understanding to solving it, and it will be okay. All right.
Yes, please.
Any question? If you have anything you are not so clear about, let me know. So okay. Then the last question. We'll just go through it, give you what and what to do. Okay. Then you look at the rest yourself. Okay. Tomorrow we are starting a new thing. We are starting with fluid mechanics. Fluid mechanics. So the first question. Okay, I guess that is it. Okay, good. The next question says that a boy on a 20-meter high cliff. This boy will continue to the step on top of the cliff. A boy on a 20-meter high cliff drops a stone. 1 second later, he throws down another stone. 1 second later, he initially drops a stone. 1 second later, he throws down another stone. Both stones hit the ground simultaneously. Find the initial velocity of the second stone. A boy on a 20-meter high cliff drops a stone. 1 second later, he throws down another stone. Both stones hit the ground simultaneously. Find the initial velocity of the second stone. Okay, so in the first situation, he drops a stone freely. So it's like holding the object and letting it to fall, free fall. Okay. 1 second, second later, he throws down. This time he didn't let it fall. Oh. He throws it. Please, this is not free falling. If it is free falling, there wouldn't be any need, okay, to demand the initial velocity of the second stone. Then straight away the initial velocity is 0. But because in the second situation it isn't free falling, that is why you are asked to calculate for the initial velocity of the stone.
Yeah.
Hello. Okay, so I think there is an omission in the question. So I modified it that take the acceleration of the second stone to be 15 meters per second square. Please, I think it's in the question though. It's in the short I sent you, but the question omitted that. Take the acceleration of the second stone to be 15 meters per second square. What it means is that the acceleration of the second stone will not be due to gravity. Of course, if you have two objects, then you let one fall and then you exert a force on another. When you are at a height, the second object will drop earlier than the